doesn't take very long before 99% of the data is outside of that sphere. The thing that we intuitively know takes up most of the square takes up almost none of the square as you get into high dimensional space. There's a really cute thing where there's a prisoner in a jail, and you put circles here that are the guards and the prisoners inside. And by the time you get up to 20, 99% of the prisoner is outside the jail. So not just, actually outside the jail. So that's how to escape from prison. Okay. So, so we have this huge high-dimensional data. Oh yes, I missed something. So generally, you have to reduce the dimensionality of the data. And if you do it right, and you're lucky, this reduces or eliminates a lot of noise, and it concentrates the signal. So this is a very good thing. Now, of course, you can always do it wrong, but that's the goal. And there's a whole bunch of methods. Principal components was mentioned before. There's a classification version of that called Fisher's linear discriminant. There's multidimensional scaling, whole bunch of feature selection methodologies. There are kernel methods. Singular support vector machines was mentioned. That's a kind of dimensionality reduction, although that's not the way it's usually thought of. So there's a bunch of things there. I like multidimensional scaling and other things that I call spectral embedding more generally. And that's where you get manifold learning. So here's the idea. You have data that sits up in some weird space up here, and you're going to use local structure. You're going to build a graph that is connected locally in this big space. And the idea is that the data sort of sits on this lower dimensional manifold. So manifold is a math term, and technically the thing that it sits on need not actually be a manifold, but that doesn't matter. But the idea is that you're sort of estimating the distance in the manifold, in the space the data actually lives. Then you can use that with a thing called spectral embedding, which is what multidimensional scaling does, to sort of unwind this thing into a lower dimensional space where all of the information has been retained, the important information, local distance information. And there's 6 or 8 dozen different approaches to this, making different assumptions on what this manifold structure is like, using more information or less information. This is the simplest, and it's really, really trivial to implement, which is nice. And I haven't talked about big data very much, except that all of our data is big. Because this is local information, the graph that you get that encodes this is sparse. So if you're using a 5 nearest neighbor, or a 10 nearest neighbor, or a 50 nearest neighbor, you only have 50 edges at every point. If you have 100 million points, that's very sparse, which means you can use sparse linear algebra sometimes. So, as I said, it tends to create sparse graphs. And there are a lot of good, strong, sparse linear algebra approaches. Basically, if you know linear algebra, essentially all you're doing is you're taking this graph, you're taking the adjacency matrix, which is the matrix that has a 1 everywhere there's an edge, and a 0 where there isn't, and you're computing eigenvectors of it. If you can compute eigenvectors, you can do this. So if you took linear algebra and you know what eigenvectors are, that's all there is to it. It's very, very simple. That's the simplest version, and because it's simplest, the algorithms are very easy to extend to very large data sets. For really, really large data sets, you need approximate methods. You don't have to have the eigenvectors perfectly. You can get approximate versions of it. My colleagues at Hopkins have used these approaches on one of these friendship graphs from I forget who, but I think it was on the order of 4 billion nodes. I think that was it. So that's, you know, that's pretty good sized. I've used it on graphs with 500,000 to 2 million nodes. So on my laptop, we're not talking using a cluster of 100,000 CPUs. There are tricks where instead of using all the data, you only use some of the data, and then you might use that information to bring in the rest of it. And there's also streaming methods where you don't look at all the data, you just look at the data as it comes to you, building your model as it comes in. So there are some other things to look at. Things change in time, so whatever you do has to be able to adapt, which means either you have to be able to retrain or to modify the models that you have, or streaming methods naturally adapt. So we've got our data, we've got it into some nice space. What are we going to do now? We're either going to cluster it unsupervised, which is grouping the data. So we're going to group the data into groups. We have to figure out how many groups there are. And we also have to decide what we mean by group. So different definitions of group will give you different clusters. We'll see an example in a minute of data that groups in ways that are sort of counterintuitive. But usually, it means internally consistent and different from everybody else. So they're clumps. That's sort of the usual definition of group. And how do you decide how many groups? Well, there are some information criteria methods that help you do that. Classification, which is also called supervised learning, there you have a class label, attack, not attack, whatever, and you want to infer the class label. And so you have to have ground truth, I mentioned that, and I mentioned some of the things you can do if you don't have perfect ground truth. But basically this, and actually this one, all you need is a way of comparing observations, but you have to have that. You have to be able to compare two observations and say these are close or not close. Fortunately, that's usually very natural in our problems. So some things you should know. You should know linear quadratic classifiers, mixture models, k-nearest neighbors, support vector machines, neural networks and deep learning, classification trees, and random forests. Well, you probably don't really need to know linear classifiers, except just to understand where they're coming from, because they probably are not going to be very useful. There. Mixture models is more general and can also give you internal clustering, which is nice. K-nearest neighbors, every student should know this one because it's trivial to implement. Any computer science student can write the code for this in 20 minutes, so that's great. And it's generally pretty good. It's almost never the one you want to go with in the real world, but it's generally pretty good. Classification trees are easy to interpret. The idea of this is the algorithm will build a tree that says, the top node, if this variable is bigger than this, go to the right, otherwise go to the left. And if you go to the right, if this variable is bigger than that, go to the right, otherwise go to the left, etc. So, if the temperature is greater than 100, go to the right. If they're vomiting, then go to the right, etc. And then down at the bottom, it assigns flu to the class of the person who's sick. So these are easy to interpret. Doctors love these because they can see why did the thing make that call. They have the problem that they're typically really bad at generalization, and they're also typically extremely variable. If you change one of the data variables, you'll get a totally different tree. And then what do you do? That's fine if you're going to build one tree, put it in stone, send it to all the doctors, and they never have to do anything. But the first time you update that tree and they have a whole new tree, the doctor's going to say, what happened to my old tree? I like that. You know, you're not checking temperature first. I always check temperature first. So that's going to be a problem. These are the best in class. There was a paper just recently came out that compared 10,000 classification variations on 10,000 different data sets and came to the conclusion that random forest is the best, support vector machines is probably just as good, and I don't think they compared these. This was a little bit, this is pretty new. I don't know much about deep learning. It shows promise, so I put it up here, but I haven't drunk the Kool-Aid on that. I'm not sure about that. But random forests and support vector machines, go with those. They will do a good job on most problems. And you guys know about how you compare, how you compute performance and stuff, so I won't go over that. So here's my toy problem. This was a Kaggle competition. So they had a bunch of Trojan code, 10,000 some observations. And they gave you there were 9 classes, so everything was a Trojan, and you wanted to group it into one of 9 classes. I don't know what the 9 classes were. And they gave you two files per each Trojan. They did not give you the Trojans, but they gave you a byte dump, a hex dump, and they gave you a disassemble, so you can look at the assembly code. Okay? Challenge. Classify a new Trojan into one of the 9 classes. Sounds like fun, right? Now, what I'm going to show you is a toy. This isn't a toy problem. 10,000 observations is not big data, but these files are huge. So there is some bigness to this, and it's kind of important, right? I mean, if you can do this, that gets you a step towards telling you things about new Trojans or new malware and things. So it's kind of important. So here's my experiment. I split the data in half, training set and test set, and I split it so that each class basically got half in each group. And then I did 2 feature extractions. The first one is a byte count histogram, 257 variables. Now those of you, you're all computer scientists, right? 1 byte, 257, there's something wrong here. One of the bytes could be question mark, rather than 07 or 3A or whatever. What does question mark mean? Presumably, the thing couldn't figure out what byte that was. My hypothesis is that somehow it knew that was unallocated memory. And so it didn't put anything, it didn't bother to read it, right? Uninitiated memory. But I don't know, that's just my guess. The other one is a document term histogram, document term matrix, for the words in the disassembly. Now, there are 170,000 odd words after you throw out some stuff. That's horrible, right? So I did one obvious thing, which was a singular value decomposition. This is, if you've ever heard latent semantic indexing, that's what this is. So I reduced the dimension down using that trick. And then I ran 2 classifiers, a 9 nearest neighbor and a random forest. Now, why 9? For no rational reason at all. There are 9 classes, I picked 9. The purpose of this was to give me a baseline, right? That would, it would tell me sort of what any idiot could do. And then random forest, my idea was, random forest would be great and would do a really good job. So we'll see. So think about this. byte count histogram seems like a dumb idea, right? What kind of an idiot would do this? The number of times the byte 07 appears in your malware hex dump, the number of times, you know, B8 appears. Why would a histogram of that tell you anything useful? Shouldn't I at least look at bigrams? Right, let's look at 16 bits instead of 8, or more general n-grams. Shouldn't I look at different sections of the code, right? When the code starts up, that might be a critical point. And so maybe I should be doing different things in different chunks. Nah, I'm just going to take a byte count. Okay? Seems really stupid. This seems stupid too. 170,000 words, right? Most of them are just, who the heck knows? They're probably memory addresses and things that I should have thrown out, but wasn't smart enough to do, right? So that's a dumb thing to do. I definitely should throw out this stuff. Certain words are more important than others, right? There are words that you don't want to see in code, and there are words that are at least indicative of potential problems, like various kinds of disk access or things like that. So maybe I should be doing things. And also, you know, bigrams or n-grams or whatever, I should be looking at the chunk of code, not just the words. So that's why I said this is a toy, right? I didn't do anything intelligent. So let's look at the data. This is a cute technique for visualizing data, the T-distributed stochastic network embedding. If you're interested, I can tell you where to get a paper on it. You can also get code freely available. And what it does is it gives you a 2- or 3-dimensional picture of your data. And these are color-coded. There's actually only 8 colors, so there's different symbols. And what you see is that, that's kind of surprising. The green things, although they don't all clump together, they all clump. There's not a lot of overlap of clusters or classes. There's a little bit, but there's a lot of single class chunks. That's kind of cool. So something to think about for a student is, do these subclusters within the thing, do they mean anything, or is it an artifact of the way we're doing this display? Now look at the disassembly. Look at these things. See, that's my way of saying there are different kinds of groups, right? This little snake, this little worm is a group. And that's a natural group that your eye picks out. But this compact blob definition of group is not going to pick it out. What do these mean? And I have a hypothesis, which I'm not going to tell you, but you see this a lot, that is twice, in these term document matrices, okay? Visualizing the term document matrices. So here's the results. This is byte count, this is disassembled, and these are confusion matrices. The thing to look at are the bottom line error messengers. Look at this. The 9 nearest neighbor, 89% correct. The 9 nearest neighbor for the disassembled, 97% correct. Heck, this stupid idea worked pretty well. And look at the random forest. Look at this. That's 98% correct on byte counts. We all agreed, well, you guys didn't actually agree, but I'm going to pretend you did, that this was a stupid idea using the byte counts. However, back to what I said earlier, almost all text document analysis comes down to you start with a word count histogram. A few people will use bigrams, but for the most part, almost everything starts with a word count histogram. They then do clever statistics to that, but the underlying information is often just a word count histogram. So you can do a lot with that word count histogram. Now, one of the things the random forest does, I didn't tell you what a random forest is. We can talk about it over lunch if you care. But one of the things it does is it gives you a measure of feature importance. So it tells you which features were important for deciding the classifications. And here they are. These are the 257 types of bytes. But you see some of them were really important. It doesn't, what the y-axis means isn't important, but it means it's a measure of importance. And you notice that there are a bunch of really important bytes. That is, having that byte in your thing, or having the number of times that byte appears in your thing is useful for telling what class you have. And then there are a bunch of things that are not as important. Now this is a univariate calculation, right? It doesn't say that having this byte and this byte is important or not important. So you don't get that correlation information. This is a similar thing, but these things, remember, these are the singular values, so they don't mean anything to us. It would take an hour to figure out what each of these corresponded to. But it does say that you don't necessarily take just the top singular values because, and this is a principal components discussion that we can have offline also. Principal components, you don't always take the top principal components if what you're doing is classification. So, ending thoughts. Security problem is non-stationary. The devices change, the software changes, the protocols change, people invent new applications, attackers react, there are new vulnerabilities. Don't build your Maginot Line. You've got to adapt to the situation. There are plenty of questions about how best to handle all these uncertainties. I like the blind man and the elephant analogy. There's all kinds of different ways to look at these problems and many different solutions to pieces of the security problems. I don't see any way to solve the security problem. You have to attack pieces. And remember, good, fast, cheap, pick 2. And what I would say is secure, usable, cheap, pick 1. And that's it. So.
Thank you very much for a very interesting talk. And we have some time for questions before lunch. Anybody? Yes.
Do you have any idea, any guess why the stupid approach works?
Why the what approach work?
The simple approach, the dumb approach of
yeah, because the bytes actually carry information about the code. The byte corresponds to, it doesn't quite correspond to an assembly language, right? 1 byte, it's not that. If I had used 2 bytes, or whatever the word length is, maybe that would actually be the same as the disassembled in some sense. But it's because, just like if you look at the words in English and you just take a word count histogram, that doesn't let you figure out what paragraph that was. But you can say a lot about what was in that paragraph just by looking at how many times each of those words. And some of the words only appear, they appear very more frequently in some documents than in others. And in these problems, you know, there's certain commands, certain underlying machine commands, which is what this byte is encoding, that occur more often in this class because they're doing more disk access, for example, than in this other class. So it's really kind of fascinating. I have a colleague who he does n-grams on characters where he'll just take I think it's 5 characters in a row it's slided across. So he's not even counting words. He's counting chunks of words. And he can do text analysis that's as good as and in some cases better than the people that do text analysis for a living. Just using that kind of information. And he can do it across languages because the same approach works regardless of the language as long as it's segmentable that way. So that's all I got. I mean, I thought it would give me 50%, 60% accuracy. And it would be something to then show off some other approach. I didn't have time to come up with another approach, so fortunately it worked out pretty well. But it's because of that importance histogram or bar chart that I showed, that there are some collections, some bytes appear more often in one class than another, or in a subset of classes than another. And that's critical information, and it's because the bytes correspond to actual machine code. And so they are relevant to what the thing does. It's not enough to figure out exactly what the thing does, but it's enough to say, oh, this is this type of malware.
Any other questions?
Do we know if a DOS or other types of attack will look different from an application?
From the code side, I don't know.
I'm just talking in general in computer systems, let's say some network application or code or whatever it is. Because to me, it seems like it's an intractable problem. How can you tell if something is an application or it's an attack?
Yeah. So, obviously they are different because they do different things. But whether or not they look differently in the data you collect. So, for example, if you look at distributed DDoSes, right, in the network, it's really fascinating. If you look at the purported source IPs that are these spoofed IPs, a lot of times they have very weird structure in them if you just plot them in time. And it's some artifact of the way these things are being chosen by the software. But something like that might tell you a lot, right? So you're getting a whole bunch of packets that that appear to be connection attempts. But if you look at the last 5 minutes of these connection attempts and you see this weird pattern, you can pretty reliably say you're under attack. You should do something. It doesn't help you on the individual packet, but it may give you information about the overall. So yeah, I mean, I think all of these attacks, they will have particular characteristics. The problem is whether or not you can collect data that allows you to figure out what the characteristics are. If they make a full, complete connection and they do everything right there, then everything is in the data that they are giving you. And so then you have to be able to look at that. And if it's encrypted, you have to either wait until it gets decrypted on your device and then look at it, or you have to come up with some other ideas.
So we have time for one quick last question.
Yeah, so kind of similar to what he asked. If we take this approach and apply this for logs, for several logs or something like that.
Yep.
In that case, when we make our feature extraction, we learn our system and implement it. The problem that becomes is that what do we do about the false positives? For example, if I just do a k-means clustering after I get my logs, and I divide, okay, these are my behavior, like these behaviors should not be for these systems, these behaviors are consistent with what these systems are supposed to do.
Right.
In that case, it becomes a little bit easier to at least address DDoS attacks and those things. doesn't
Right,
help
yeah.
us to solve it, but what about the false positives, which we get like quite a lot?
Yeah, so logs are really logs. You should be looking at the individual log entries as opposed to the log file, right? It's not the log file that's an attack. It's the collection of entries that are going into it. So it's a smaller data problem. You might look at a window of the last 7 log entries or something. So it's much sparser. But you're right. Unless you can unambiguously say, if something gets root, that's an attack. And it's always an attack. Unless you have simple rules like that that you can rely on, any one of these is going to have false alarms. The question is whether or not you can play that rock curve trade-off. Drive the false alarms down without losing too much on the detections. And that comes down to doing a better job of the feature selection. If you can figure out what are the correct things to use to make that decision, then you will get the best that can be done. The problem is we don't know what those correct things are. So we have to use these approaches that give you an estimate of what those are, but they're they're biased by the data that you can use to make that decision. So,
well, thank you very much, David. Couple of announcements. During the lunch, we have a poster session, which is right next to the computer science department office, and we are giving best student poster awards, couple of them. So I would encourage people to get the evaluation forms from our staff members who are in the office and score the posters, not just attend listen to what the students have to say. Okay? And lunch will be served right across the hallway in the same room that we have the coffee break. And I think we have enough lunches for the registered participants and maybe a couple more.